Okay, so we are going to look at a conservation, a conservation of energy problem that involves potential energy, kinetic energy, and elastic potential energy. Gravitational potential energy, elastic potential energy, and kinetic energy. Okay, so imagine you go into an arcade, and in that arcade there is a vertical pinball machine. So pinball machines are super awesome, and you see this vertical pinball machine. So what that vertical pinball machine looks like, in case you don't know what a pinball machine looks like, is it's this vertical wall encased, and you have a spring and a plunger here, and a ball sits on there, and then the ball, you pull that plunger down, so you stretch the spring, and when you release it, it shoots, the ball follows it, it shoots the ball up and around a track, and then it releases into this box of buttons and things, and ding, 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 and it falls down. Okay, we're not going to worry about that second half of that part. So the question is, if you want to pull that plunger down just enough so that the ball reaches the very, very top of this track, and we're going to pretend, for the sake of ease in this problem, that the track just goes straight up, shoots up the middle, let's say, of the pinball machine, goes straight up so that it reaches the very, very top of that track and stops. How much do you have to pull that plunger back? How much do you stretch the spring in order for the ball to stop at the very, very top of the track? Okay, so that's our question. We are going to say that the ball has a mass of 0.8 kilograms. I'm making this problem up as we go along. Ball has a mass of 0.8 kilograms. The spring constant of the spring is 250 newtons per meter. And the height of the pinball machine is, let's say it's 1.1 meters. All right, so that's our situation. So how do we know how high it's going to go? The second part of the question, so part A, is how high will the ball go? Well, we don't want to know how high the ball will go. We want to know, wrong question, we want to know how much do you extend the plunger so ball stops at the top. And the second part of the question, part 2, is how fast is the ball going when it leaves the plunger? Okay, so how fast is it going when it starts to travel upward? All right. Now, we could actually do this a couple of different ways, and that's the beauty of energy and motion and forces. They can all interrelate. You can do them whatever you're most comfortable with. But I want you to be thinking about conservation of energy and using conservation of energy ideas to solve this problem. So what do we know about the conservation of energy? Well, we know that the total energy at any point in time has to be the same. So let's define our initial as at the very bottom with the spring, the plunger pulled. So we'll call it the plunger. Okay, so pulled at whatever that distance is to get it to be at 1.1 meters at the top. That's the total pulling of the plunger. That's where it's going to start. And our final is when it stops at the top. Okay? So if we think about this as an energy situation, our total energy initial has to equal our total energy final. So our total energy can be made up of gravitational potential energy, spring energy, because I have a spring in this problem, and kinetic energy, initial for all those. And that has to equal our total gravitational potential energy plus our spring potential energy plus our kinetic energy at the end. All right. So let's look at setting our height reference and then thinking about where some of these do we have values for these energies at these various points in time. So let's set our height reference at that lowest point. So height equals 0 at extension. Okay, so we're going to set the height equal to 0 at the extension point when it's fully extended. So if my height is 0 at the beginning, then my gravitational potential energy is going to go to 0. And I also know that the ball's not moving right before I let go of it, so my kinetic energy is going to be 0. So by being clever and setting that height at the end then of that extension, then my total energy is all in the spring. Now, we have to be very careful here as we move forward. Now, at the end, when it's at its height, now, we said the height was 1.1 meters, but keep in mind this is at the spring rest point. Because remember, we're trying to decide where that, how much we have to pull that down. So my gravitational potential energy at the top, if my 0 is at the extension, is going to be the mass. Oh, let me use the color that I've been using. The mass times g times the final height, where that final height is going to be the 1.1 plus whatever my change in x is for the spring. Okay, so we have to add that energy in because it's a little higher than where it started, where it was defined as the height of the track. Okay, the spring is no longer in play, and if I stop at the very top, there's no kinetic energy either. So I end up with the kinetic energy, or excuse me, the potential energy of the spring, which is 1/2 k delta x squared. And that's going to equal my mass times g plus 1.1 plus delta x. All right? So I'm interested in how much compression or extension, delta x, of the spring. So I have 1/2 times k, which is 250, delta x squared, equals 0.8 times 9.8 times 1.1 plus delta x. All right, so we have 0.5 times 250. So I should have been able to do that. So I have 125 delta x squared is equal to 0.8 times 9.8 times, let's just say that's its own thing, 7.84 times 1.1 plus delta x. So 125 delta x squared is equal to 7.84 times 1.1, 8.624 plus 7.84 delta x, and I'm going to end up with a quadratic. So we have 0 is equal to minus 125 delta x squared plus 7.84 delta x plus 8.624. And I have to solve this quadratic equation for delta x. All right, so how do I do that? Well, I use the quadratic formula. Delta x is going to equal plus or minus b squared 7.84. Nope, that's not right. It's not the quadratic equation. What am I doing? It's the opposite of b, minus 7.84 plus or minus the square root of 7.84 squared minus 4 times a minus 125 times c, 8.624. 624 all over 2 times A minus 125. All right, so let's do that calculation. I did not have this prepared since I just made it up. So we have, I'm going to do it in steps. Delta x is equal to minus 7.84 plus or minus the square root of 7.84 squared, which is 61.4656. 4 times 125 times 8.624 plus, because those two negatives go away, 4312 all over negative 250. So 4312 plus 61.4656 square root. I have negative 7.84 plus or minus 66.13 all over negative 250. And in this case, my delta x has to be positive because I'm looking at the total amount of compression or extension in this case. So that's going to be the minuses for all of this. So minus 66.132 plus negative 7.84 divided by negative 250, and I get delta x is equal to 0.296. So my delta x is 0.296. The delta x of how much we should extend the plunger. 29 centimeters. That's a lot. That's a lot of pull for a pinball machine, but I'm making these numbers up as I go. All right, so you're understanding that idea of conservation of energy. Okay, now I have to erase part of the board because I have way too much stuff. So I'm going to put this here as delta x is equal to 0.296 meters. And then we'll look at the second part of the question, which is how fast is the ball going when it leaves the plunger, when it releases off of the spring. So that too is an energy conservation problem. Or we can use conservation of energy to solve that problem. So let's look at that. So for part 2, our total energy initial has to equal our total energy final. And now in this case, our initial is at the bottom of the extension, and our final is when it leaves the spring. All right. So same process. Our total energy, we could have gravitational potential energy initial. We could have spring potential energy initial. We could have kinetic energy initial. That has to equal the gravitational final potential energy plus the spring. Oops. I did it again. These markers are going. Let's use a different color. Spring final potential energy plus the final kinetic energy. All right. So at the very bottom, we do not have gravitational potential energy because we've defined that extended point as being 0. Our spring potential energy does exist, so we have 1/2 K delta X initial. But we don't have any kinetic energy because it's sitting there at rest before we let go of it. All right. Then at the end of our spring, we do have a little bit of potential energy, so it's mass times the gravity times our height in this case at the end. Our spring is out, so we don't have any more spring, and we are moving a little bit, which is exactly what we're interested in. All right, so it's recognizing what energies exist both at the beginning and the end, then using that information in our conservation equation. So now we can start plugging in the numbers. So we have 1/2 250 times delta x, which we determined to be 0.296, is going to equal the mass, 0.8, times 9.8 times 0.296, plus 1/2 the mass, that should be, there we go, 8 times V final squared. And so all we got to do is solve for V final. One equation. Pretty slick. So 0.5 times 250 times, oh, this should be squared, 0.296 squared is 10.952 equals 0.8 times 9.8 times 0.296, 2.32 plus 0.4 V final squared. 10.952 minus 2.32, 8.632 equals 0.4 V final squared. Divide by 0.4 and take the square root. V final is equal to 4.64 meters per second. So in one fell swoop, we can solve for the velocity at the end. All right, conservation of energy is pretty powerful. Don't have to do all that force analysis. Don't have to do, oftentimes, we don't have to do kinematics. We have seen some problems that mix kinematics and energy, just to remind us of those tools, but it makes the problem solving much quicker. All right, nice job.